we would like to welcome Dr. Reza Javaherdashti to our seminar in C2E2. So Reza is coming from Eninco Engineering in Netherlands. He's a general manager there. They are a consulting and engineering firm that work with paint and coating systems. But I think, Reza, you will give probably a proper, deeper introduction about you. You have really wide and kind of experience in the field, from kind of international experience. But just a short, so Reza holds a double degree in material science and metallurgical engineering. And he is an internationally renowned expert in microbial corrosion with more than 20 years in this field in both academia and industry. He will give a deeper introduction about his experience and background. Action. So Reza, the floor is yours.
Okay, thank you very much, Yasna. Thank you very much, Terry. Good morning to you all. The title, I hope that everyone can see the my screen, the slides. Good. Yeah. All right. The title of the presentation today is Management of Corrosion and Microbial Corrosion on Solar Panels and the solution that we can offer. Now, all right. First of all, we need to, okay. First of all, I'd like to remind you all again about the cost of corrosion. When we talk about cost of corrosion, we really don't mean a specific industry. It could be all industries, from oil and gas industry to electricity producing industry, everything. You would see that annual cost of corrosion to all these industries all over the world, altogether, the cost is more than the cost of all the natural disasters, such as but not limited to fires, tsunamis, hurricanes. So corrosion is a very important issue. Unfortunately, I don't have enough time to share with you some examples of ecological disasters that has happened due to corrosion. However, all I can tell you at the moment is that corrosion has both serious ecologic as well as economic unwanted side effects. I would like to briefly introduce myself. I am the general manager of Eninco Engineering, which is located in the Netherlands. I am a certified lecturer by ASME, as well as Society of Petroleum Engineers. So far, I have had more than 5,000 hours of teaching corrosion management and microbial corrosion. This MIC that you see stands for microbiologically influenced corrosion, by the way, to various industries around the world, from South Africa to the US to Australia and many other countries. I have been involved in more than 400 projects as both the manager and problem solver. Thanks to God, so far I have not made anything go wrong. I have some books published or to be published by well-known publishers such as CRC Press, Springer, Wiley, and they are mostly about corrosion management and microbial corrosion. I was a member of ACA, that stands for Australasian Corrosion Association Australia, NACE in the US, that now has become AMPP, and also Institute of Corrosion. These are some examples of books that I have authored or co-authored. For your attention, perhaps on upper left, you see a red book that reads Microbiologically Influenced Corrosion and Engineering Insight. This book has been downloaded from Springer website itself, I guess more than about 4,000 times so far. And these are two books that I published in 2020 regarding biological treatment of microbial corrosion and failure analysis of microbiologically influenced corrosion. It is also my ASME certificate for teaching the matter. Now, underlying philosophy of this presentation. You see, when we talk about corrosion management, we could have basically two approaches. One approach is system approach, and another one is materials approach. What do we mean by that? When you go for a system approach, it is corrosion in a given system that is of interest to you. For example, when you go to industry, people may say that, I have corrosion problems with my jet engine. What can I do? Or I have corrosion problems with my, power plant, heat exchanger. You know, specific industries, specific systems. This is basically what you will be faced with when you talk to industry. They say that, do you have enough experience in dealing with corrosion in, for example, boilers? And if you say no, but I know that boilers are made up of carbon steel. And if I know under what conditions carbon steel can be corroded, then it doesn't matter what industry it is or what system in which this material has been used. Okay, then they say, okay, this means that perhaps we cannot recruit you. Materials approach, however, is looking at the material itself. As I just mentioned, as a materials scientist, when you approach or when you try to highlight the conditions in which a certain material corrodes, it really doesn't matter if the industry is a power plant, a refinery, it is based in, I don't know, the US or in the UK, doesn't matter. As long as you know what the material is and under what conditions actually things can go wrong and the material starts to corrode, you are on top of the problem. In this presentation, I will try to use a mixed kind of approach, system and materials. Bear this in mind so that when we talk about corrosion in solar panels, you should not be surprised, because as I said, I will try to use a mixed approach. The current problem is this. Photovoltaic solar panels can be covered by dust, soil, salt, many things. And this can actually reduce their efficiency in producing power, in producing electricity. Even a thin layer of about 10 micron in diameter can basically make things go wrong for a solar irradiation system. Let me give you an example why this is a serious issue. Efficiency of photovoltaic, PV stands for photovoltaic. Efficiency of PV systems is around 15 to 20%. Now, imagine that due to factors such as dust or soil or anything of that sort, the efficiency of your solar panels could go down. You could experience losses like 20, 25% or even more. This means that the solar panel, although it is a clean energy, although it is a very, it is not as sophisticated as the industry we have, in industries we have, such as oil and gas, etc., etc., due to having dirt or being in a position that absorbs dust and other soiling materials can easily lose its efficiency. So it is a very important issue to find ways how to basically prevent soiling, so to speak. That means covering the surface of the panel with dirt. There are levels of standards that currently are used to address corrosion. These are in association with IEC 61701 standard, and they are basically uh, classified into 6 levels. As you see, level 1, it says that corrosion resistance if salt is available to the uh, solar panel, a little bit. And it is not a continuous process of getting, for example, salt on the solar panel. If it is the situation, then you would say that the solar panel I have manufactured has IEC 61701 level 1. Then it goes upper to level 3, level 5, and level 6, which is the most widely used standard in manufacturing solar panels, states that panels with this level of standard, they have survived 12 days of testing for exposure to a salty environment with less than 2% decline in power output. So you basically expose your panel to an environment with a lot of salt in it for 12 days, and then you measure that even if you have such severe conditions, the loss in power output will not exceed 2%. Most of solar panels, PV solar panels that are being used these days, do have level 6 standard. However, there have been reports that due to particle accumulation during drought seasons, or which is called soiling, particle accumulation in these cases are referred to as soiling, you could lose 0.1% of the power production. And while it may sound like a very tiny, unimportant issue, you would see that estimated cost of losses due to soiling could reach by $4 billion by 2022. It is an important issue, and as we are basically trying to become less and less dependent on oil and gas resource of fossil, for that matter, fossil fuels, and move towards renewable energies, having a cost of $4 billion per year, by year 2022, due to soiling, is a significant issue. There are a lot of causes for dust accumulation. Here you see that the dust type, the box in the middle, it shows some of these factors. And if you go down, the third factor is bacteria, which is in relation with industrial area, as well as air pollution. So it is this matter that is important to us. The role of bacteria, in addition to other types of degradation. In addition to factors such as soiling, it is quite likely for certain types of bacteria which are resistant to adverse conditions to survive on these panels. The role of these bacteria settlements, which can be referred to as biofilms, could account for a decrease in efficiency by 11% after 18 months. These are reports that actually have shown these figures, roughly equivalent to 0.2% per day, which is quite a high number. The amount of efficiency decreases when bacteria are involved, are quite significant should they be the only contributing factor for covering the panel's surface. This means that if bacteria alone were responsible for covering the panel surface and creating soiling, then we could come with a deficiency or loss of efficiency by 11% or so within a year. Imagine that in addition to bacteria, you have also other covering materials such as dust, snow, etc., etc., that would again would increase these unwanted impacts. Solar panels, you can basically see three types of corrosion processes. Salt corrosion is one of them. Galvanic corrosion, I will explain galvanic corrosion in a moment, and moisture ingress. Why moisture ingress is important, we will see it when I talk very shortly about electrochemical corrosion. Corrosion can affect solar inverters, electrical gadgets. Corrosion can affect wires, contacts, and junction box in the solar panels. Mind you, these electrical instruments inside the panel, they are being made up of several metals. So it is also possible that due to ingress of moisture and basically water, you would come up with a battery, which is underlying principle of galvanic corrosion, and then you get corrosion. Panel frames are normally made up of marine grade aluminum alloy, again a metal, and this metal can also corrode. So it is not that you have a silicon wafer framed with a metal, then you get sunshine and hoo-hoo, we have energy produced. No, this metallic frame can be corroded itself. The electrical connections and gadgets inside the panel can be corroded, and the surface of the panel could be covered by biological or non-biological particles. So in order to increase the efficiency as much as possible, we have to address all of these seemingly different processes. Well, as I said, corrosion is itself an issue. And for that, I have to go through electrochemical corrosion very shortly. This is not even corrosion 101. But that, I hope, can give you an idea of what we are talking about. Corrosion is a thermodynamic process. What it means is that you take out the metal from its ore via crushing the ore, then you take it to metallurgical complexes where you insert extra electrons via extractive metallurgy processes, and then you get metal with a very high purity. For example, in case of iron, you could get purities like 99.995%. And then when you have this iron, then you apply alloying elements, carbon material, etc., so that you will end up with either steel or cast iron. And mind you, in industry, we don't have anything known as iron. Iron only exists under laboratory conditions. In industry, you either have steel, stainless steel, or cast iron. That's it. Anyway, the steel thus produced has electrons that had been inserted to it via extractive metallurgy processes. So these electrons are extra electrons that are not from the metal itself. They are like unwanted guests. Therefore, the metal starts to find ways to get rid of these extra electrons. This process during which electrons are being liberated, I mean, these extra electrons are being liberated so that the metal again comes back to its ore, is called corrosion. And the ore that is produced after going through corrosion is corrosion or corrosion products. When we talk about iron ore, for example, this ore is basically a combination of iron with carbonates, iron with sulfates, iron with other chemical elements. And corrosion products are also the same. Corrosion products could be oxygen, like iron oxide, like hematite, Fe2O3, like magnetite, Fe3O4, like iron sulfide, etc., etc., etc. So corrosion is basically a backward travel in time, something like Back to the Future, but I don't know which one, 3, 4, 5. When you have corrosion, the material gets back to its origin. However, when the metal corrodes, it also loses its mechanical integrity. So it is not as strong. I mean, a corroded piece of steel is not as mechanically stable and powerful as its original steel. Electrochemical corrosion can be demonstrated in many can demonstrate itself in many processes, such as from left to right: stress corrosion, cracking, galvanic corrosion, metallization, atmospheric corrosion, corrosion under insulation (CUI), and microbial corrosion (MIC). And the ones with these blue circles around them are basically the main corrosion processes that could be affecting PV solar panels. Atmospheric corrosion is also, or could also play an important role, but the ones with these blue rings around them are the most important corrosion processes. What is corrosion? You have metal that when you put it into a corrosive environment, it starts to corrode. What does it mean? It means that when you have copper and, for example, iron, based on their potentials, they start to release and receive electron. Okay, if they release electron, that metal is called an anode, and if they receive electron, that metal is called a cathode. For that, you have to have an environment through which ions will be moving around, and that is called electrolyte. And because corrosion is only used to address metals, then basically electrons will transfer from anode to cathode via the metal itself. It may be interesting to know that when we talk about electrolyte, I can give you an example, like if you compare seawater with distilled water, corrosion in distilled water could be much, much higher than seawater. And this is one of my questions to you. Why do you think it is so? In distilled water, you can assume that you have, better to say, in demineralized water, you can assume that you have no ions. However, in seawater, you obviously have a lot of ions. So what it is that makes demineralized water to become more corrosive than seawater? Think about it, and we will get back to this matter later. Electrochemical theory is one of the 3 tricks that we as corrosion scientists apply to basically realize, to define anode and cathode. we assume that the potential of hydrogen for giving electrons, here, sorry, it is reduction, for getting electron is 0. We assume that protons, in order to become hydrogen, okay, they standard potential is 0. Actually, it is not. We assume that it is so. Therefore, any reduction potential above this 0, which becomes a positive number, marks a noble metal, a metal that would not corrode. At the very top of this table, you see Au, gold, which has the highest positive potential. This means that gold will not corrode. And below this 0, you will see a lot of reactions with negative sign potentials. This means that these are very, very active, and therefore they can be corroded easily, and that we can refer to as anodes. If, for example, you pair, say, copper here on the on top of copper with a positive potential of plus 0.342, just 2 reactions above hydrogen, copper, and say, I don't know, nickel, for example, below the hydrogen line with a negative potential of minus 0 volt. Then if you just pair these two, you will see that copper will become cathode because it has a higher potential, and nickel, for example, will becomes an anode. You can continue with such electrochemical series scale and see how it goes. Galvanic corrosion is basically defined based on more noble and less noble metals. This way, you can also have a combination between ferrous and non-ferrous materials. So if you have two dissimilar metals joined together, then you will end up with galvanic corrosion. Microbiologically influenced corrosion is electrochemical corrosion per se, in which effect of bacteria and in addition to other microorganisms is well touched. And it is basically the reason that microbial corrosion and electrochemical corrosion are to be addressed together, is because the electrolyte for both of them is water. And this is the reason why we have to know both. Electrochemical corrosion happens in water. Microbial corrosion also happens in water, and also water provides food for microbes. That's the main point, that when you look at microbial corrosion, you have to also consider electrochemical corrosion. Life, as we know, can be divided in 3 kingdoms, and bacteria and their cousins, archaea, are basically prokaryotes that most of the time, from a corrosion point of view, corrosion engineering point of view, cause a lot of problems for us. So that in order to address corrosion-related bacteria, we have to also address corrosion-related archaea, because they are just like left and right hands. They are similar, but they are not the same. Microbiologically influenced corrosion is an electrochemical corrosion that is initiated, enhanced, or even inhibited under certain circumstances by bacteria. Almost all engineering materials, from metals to glass even, and concrete, are exposed to MIC, microbiologically influenced corrosion, or MID, microbiologically influenced deterioration. Why I make this distinction? Because, as I said, corrosion is to be addressed only for metals. For non-metals, you use deterioration. There are many ways to address MIC. Some people may call it as microbiological influence corrosion. Some people may say microbial corrosion. It doesn't matter. As long as you don't address it as bacterial corrosion, you're on right path. Bacterial corrosion implies that it is only bacteria that can induce corrosion, which is not true. Biofilm was in fact, biofilm is referring to bacterial establishments, all right? It was coined in 1978, and it is defined as a matrix enclosed bacterial film in which bacteria are sticking together and via several processes can induce corrosion. However, the very term biofilm is not correct because it is neither 100% biological nor it is a uniform film. That's why in my paper in 2020, June 2020, I suggested the word temenos instead of biofilm. Temenos is a Greek word that means cut off. It is to emphasize on the fact that under biofilm conditions are far different from conditions beyond the biofilm. Beyond the biofilm, you could have pH like pH 7. Under the biofilm, you could have pH 3. All right. So temenos, and how it happens, it basically happens in 6 what you call it steps. In step 1, you have planktonic bacteria. These bacteria, then we call about, when we say planktonic bacteria, we basically address bacteria that are swimming around in water. The same thing could happen with bacteria flying basically in the air. So they just sit on the surfaces, as you will see in here, slide, step number 2, the bacteria become sessile bacteria. This is motionless. It means motionless bacteria. And when they start to attach themselves onto the surface, step 3 and step 4, then you will see that the biofilm starts to become thicker and thicker. And by time, as you will see in step 5, some of these bacteria basically will die off because they do not receive enough oxygen, enough food, etc., etc. And by any any force coming from the environment, a part of them will basically will be taken off, and you will have venues of high oxygen and low oxygen. Beyond the biofilm here, I'm referring to step 5. Beyond the biofilm, it is low oxygen venue, and here where the part of the biofilm is gone, we have a high oxygen spot. And when you have low oxygen pressure spot, you will get anodes, and their pitting and corrosion will start under the biofilm. Now, just to measure if you have been coming with me, did you recognize the mistake I deliberately put in the previous slide? Yeah. Here I said, I mentioned the 6 steps involved in formation of biofilm, and I said that when a part of the biofilm is taken off because of external forces, you will end up with what we call in electrochemical theory as differential aeration cells, where you have spots with high oxygen pressure and low oxygen pressure. When partial pressure of oxygen is low, you create anode, and when the partial pressure of oxygen is high, you create cathode. And where you have anode, then you get enhanced corrosion in the form of pitting. So with these with this explanation, I hope that you have found the mistake that I deliberately made in this slide. These are some examples of bacteria I have worked on, especially sulfur-reducing bacteria on the top and iron-reducing bacteria, but there are a lot of them, more than 15 groups of them, and many more to come. These are some industrial examples of biodeterioration. Here it is the interior wall of a cooling tower made up of composite. As you can see here, the composite itself has been covered with a film of algae. And this power plant actually has been using wastewater for less than a year. Just to save water, they turned into using wastewater, and within less than a year, this is what happened to their composite made structures. It is also a close-up of concrete column covered with a thick biofilm. Yes, all right, here instead of biofilm, I was supposed to say temenos, but anyway, this is a very important situation in power plants because this film is kind of serving for not only harboring corrosion-related bacteria, but also pathogenic bacteria. Microbial corrosion is not a very easy issue to handle. And in order to explain it, when I was trying to model it, I used fuzzy logic in order to basically predict how we can rate corrosive effects of bacteria. All right, there are basically 6 ways by which corrosion can be addressed, like cathodic protection, anodic protection, use of chemicals such as inhibitors, coating, etc., etc. And here I'm going to just address coating in this presentation. By coating, what you do is basically you blind the anode from seeing the cathode. In other words, you coat the material so that anode and cathode cannot see each other, nor can they see the corrosive electrolyte outside. That's why coatings are of very, what you call it, significant. Here, you can see that there are 3 elements involved in electrochemical corrosion: anode, cathode, and electrolyte. When you apply coating, you will basically cause the electrolyte not to become in touch with anode and cathode. On the other way, anode and cathode will be basically cut off from each other. That's why a good coating can basically guarantee having a good corrosion management system in place. Now we come to the solution that we have for soiling. Why soiling? I explained all of these just to address that soiling, either in form of biofilm formation or dust accumulation, etc., is a very important issue, because in addition to electrochemical corrosion and microbial corrosion, they could they could significantly contribute to basically lowering the efficiency of solar panels. And for that, we have anti-soiling coating option that we have produced here at Eninco. I don't want to appear as a sales engineer. I'm trying to just address the state of the art as much as I can. The current methods to basically recognize the problem or to rectify the problem is by using either physical inspection. You send someone to just look at the surface of the panel. If he sees any dirt or soil, dust accumulation, he would report it. or you say you use monitoring services for that. In other words, you can either cleaning the solar panel yourself, good for you, go for it if you could, because in a solar panel farm, there are many of these solar panels sitting, and cleaning each of them by yourself may take months. Another option is using solar panel cleaning services such as drones or robots, as well as use of nano cleaning products and self-cleaning products. Our solution is a self-cleaning, smart, super hydrophobic hydrophilic coating. In this coating, the main binder is derived of cyanoacrylate modified with PDMS, and then it is filled with manganese oxide polystyrene. Just imagine you have very small balls, nano-sized balls, and then you fill it with these chemicals, and these chemicals will be released over time to basically make the surface super hydrophobic. Why? When it becomes super hydrophobic, it will not allow formation of biofilms or what you call it, moisture, so that this moisture will later act as a either as an electrolyte or as a source of nutrients for bacterial adhesion. Advantages of these coatings so far we have measured in the lab is that they are natural-based coating with low VOC. VOC stands for volatile organic compounds. The lesser it is, the more eco-friendly it is. And these coatings have a very low VOC. Then they are very easy to apply. You don't need special tools for application. They can stay on the panels for quite a long time. Our records show at least 5 years. They are self-cleaning, and they have the so-called lotus effect. Lotus because it is referring to the super hydrophobic properties of leaves of this plant, and that's why we also call it as lotus. Repellent of water and dirt it is, therefore you will not have accumulation of dirt. Maximum resistant to soiling because of these properties it has. It is completely, it gives complete protection above solar panels exposed to the weather. It really doesn't matter if you put your solar panel near the sea or in industrial zone, wherever. With this coating, we will see that it has a lot of positive points, such as resistance against UV and also dust collection. And because it doesn't allow formation of water, it doesn't allow bacterial adhesion, and it is also cost effective. It is not very costly because one of the drawbacks of new technologies is that when they come to the market for the first time, they have very high prices, and then by time they start to become cheaper and cheaper and cheaper. Just remember the first generation of computers or smartphones. But in our case, it is very cost effective. It is not too costly, too expensive, and most of all, it increases the energy efficiency at least 1% and more. And as you just saw, when we talk about photovoltaic structures, we are basically walking on a very narrow line. Last but not least, our aim from these presentations, I mean, when I say these presentations, I refer to the presentation I had 4 days ago and the presentation now, is to basically establishment of a research group that could have the following 7 topics as the main axis of research. Microbial adhesion on solar panels. We cannot say that our technology is 110% complete. Definitely there are aspects of it that needs more research. Microbial corrosion of engineering materials. We don't still know the whole story about microbial corrosion. There are a lot of theories that try to address microbial corrosion, but none of them are still the most appropriate one. Biodegradation of polymers and composites, the same. We always think that polymers and composites are resistant to bacteria and microbes. This is not true. And we could have another, what you call it, webinar on that. Yeah, polymers and composites are not resistant to microbial degradation. Antimicrobial coating and nanobiomining. Last time I had a very short talk about what nanobiomining is. It is basically extraction of nano-size magnets from the body of the bacteria. They not naturally produce it. Fuzzy modeling of MIC, I can assure you that for the first time, fuzzy logic and fuzzy calculus have been used in order to address a natural and very complicated process such as MIC, and also use of bacteria for biofuel cells. Last time in my presentation, I mentioned Clostridia. These bacteria are capable of producing ample amounts of hydrogen. So they can be used for producing hydrogen, and then this hydrogen can be used in many applications, such as, for example, eco-friendly engines, etc., etc. Okay, thank you very much for your attention.
Thank you so much, Reza. This was very interesting, as the same as last time. Related, but not the same webinar last week in the materials engineering department. So I would like to ask anyone who has any questions to, I guess you guys need to type them in the Q&A box. So please send those, your questions through the chat, and hopefully I will be able to see them. In the meantime, as okay, we already have. What other energy applications, not solar panels, does MIC affect? Aubrey is asking.
Okay, MIC can affect almost everywhere where you have water in liquid form at a pH of 2 to 7, where this water is stagnant or is moving with very low velocity, and it has enough food to let bacteria survive. If we want to talk about the industries, power plants, all types of pipelines, nuclear power plants, aviation industry, bridges, desalination units, water and wastewater treatment units. They are all examples. These are examples of industries in which MIC could be a big problem, in addition to being a problem for PV solar panels.
Thank you.
You're welcome.
Any other questions, guys? as the other questions are arriving, let me ask one of, I have here a whole list, but I'll just limit myself to a few maybe.
Okay.
So you were mentioning, that we need anode, cathode, and electrolyte. So in PVs, what would the electrolyte be? Is it let's say, rains and then it forms some kind of film, or what is the electrolyte in the case of PVs?
In case of PVs, there could be examples of electrolytes such as the moisture in the air, and also rain, snow, and things like that. Most of the time, however, we refer to electrolyte for PVs as the moisture in the air.
Okay. Yeah, okay, that makes sense.
Mhm.
And does the corrosion only affects the metallic kind of frames and contacts, or do also semiconducting materials, I guess, degrade or
Yes,
even
both,
corrode?
both,
Both?
both. I mean, it can potentially, corrosion can potentially adversely affect all metallic um, uh, parts of a PV panel, from the semiconductor um, instruments that are inside the box to the metallic frame around it. Um, the problem is that we, I mean, most of technologists working in this area are under the influence that, okay, because we are using, say, aluminum, marine grade aluminum, then we don't need to become kind of, to be worried that corrosion would affect the frame. But it seems that we forget that even the ships also corrode that have been made up of that kind of aluminum. The point is that as human beings, we have to go for energy producing options which are safe as well as eco-friendly, and also with very low maintenance costs.
Yeah.
Because high maintenance costs can also happen in fossil energy industries quite easily. Therefore, if we make PV solar panels, we have to be sure that after 1 year or so, we don't need to pay for its maintenance. That's why I think that addressing corrosion and microbial corrosion for PV solar panels is a very important issue.
Yeah, sounds definitely like it is.
Mhm.
Does anyone have any more questions? Please don't be shy. I'm sure there are a lot of questions, but our audience seems to be shy today.
Oh, okay.
That's okay.
Um,
Maybe, yeah, go ahead.
maybe I can use this opportunity to answer the two questions that I asked.
Yeah, actually, yes.
Yeah. In the first question, if you remember, we asked about, I guess it was this, I think it was.
I forgot.
Okay. I will,
You probably have a few hidden questions, so
yeah, yeah. But one thing is that, okay, about this uh, electrochemical standard scale. If you remember, I said that this is one of the three tricks that we have in electrochemistry to address anode and cathode. Electrochemical series, or a so-called standard hydrogen scale, is useful, but it doesn't have any value for industry because it has to be constructed under standard conditions, such as temperature 25 degrees C, atmospheric pressure of 1 atmosphere, blah, 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 that most of the time they are not reachable in industry. That's why, in addition to electrochemical series, we have two more hidden weapons to let us determine anode and cathode. The other one is the so-called galvanic series. Galvanic series basically ranks material based on the environment and a standard temperature. You construct a galvanic series for, say, 25 degrees centigrade, only for seawater. Then you say that, okay, if the environment is seawater and the temperature is 25 degrees centigrade, then this metal will become anodic with respect to that metal. And if the temperature changes, then we use electrochemical theory, such as using Nernst equation, to basically adjust the series. The third trick is what we call as Purvey diagrams that will allow us to predict what material could be anodic and which one could be cathodic. This is the second hidden question.
Can I just interrupt you? Sorry. Actually, Professor Agrios remembered the actual question, which was why deionized water is more corrosive than seawater, and he is guessing that it's because it's been stripped of carbonates. It is unbuffered and subject to wide pH swings. So you can tell us if that's correct.
Well, to some extent.
Your opinion, yeah.
Yeah, to some extent. Some years ago, because my favorite cartoon is The Simpsons, and I have got a lot of ideas from The Simpsons. One of them was when in one of my classes I was trying to answer to the same question. I put two cartoons of Simpson, Homer Simpson. In the first one, Homer Simpson was quite hungry and was attacking his beloved donut. In the second one, he was full and he was not even looking at the donut. I said that when you have demineralized water, it is stripped of all ions. It is like hungry Homer Simpson. So in case it sees any ions due to external corrosion or anything of that sort, it will attack on getting as much ions as it can. In seawater, you already have a lot of ions. And that's why in industry, one of the most challenging corrosion questions is to keep demineralized water as ion-free as we can. Most of the time, this is not possible because when this demineralized water comes into contact with air, it starts to dissolve carbon dioxide, which will produce a weak acid, and then this weak acid will go through a lot of chemical reactions. The end result being that you will get corrosion. In oil and gas, for our audience, in oil and gas industries, one of the most terrifying corrosion problems happens with what we call as sweet corrosion, where it is the corrosive effect of CO2 that causes a lot of problem, and it is very hard to predict, although there are models for that. And what about the mistake in this slide? As you may remember, I said that when we have a part of, look at step number 5, here a part of the biofilm has been taken off. Therefore, oxygen is higher there in comparison to its adjacent point. So you have two venues, one high oxygen pressure another one low oxygen pressure. Therefore, the pitting, the corrosion, enhanced corrosion, is to happen under where you have low oxygen pressure. In other words, in step 6, the arrow must have moved to show the heating under the biofilm to the right side, not where high oxygen pressure exists. This was a little bit tricky, but I normally use it in order to show that knowing electrochemistry is a must to address microbial corrosion correctly. It is not just biology.
Thank you. I
You're welcome.
did not guess the right answer. I think we should be wrapping up, but there is one more question from Terry. If you can answer. So she says the average population that is getting solar panels mounted on their homes, they don't take into account the degradation. What is the recommendation for these people to help them to reduce the maintenance of their panels? Most people do not want to pay the extra cost of the maintenance or climb on their roofs to clean the panels.
Well, if they can find any way to basically keep the surface of their solar panels as dry as possible, then they will not need any other costly option. But this is not possible, because this means that they have to move their panels either to Sahara or to the moon, where you have no moisture in the air. And by the way, don't forget that the amount of microbes or bacteria that, I mean, not the amount, but the type of bacteria that are capable of covering the surface of the panel is not fixed, because they are flying with air. So, for example, my house is here with my solar panels on the roof, everything goes well, and then 1 kilometers, 10 kilometers ahead, you have a factory that, for example, produces, I don't know, sausage. That factory, for the very nature of its production, is highly contaminating the air around it. And these bacteria are very easily moving to my house area. Just very shortly, let me tell you a story. Once I had a project in Papua New Guinea, which is an island in the ocean, I think in Pacific Ocean. There we have a lot of microbial corrosion problems happening on the jetties, where the factory was basically exporting its products. And there were basically no obvious source of bacteria for that. Then when I got there, I had a survey for the nearby factories, and we found out that in the nearby there was a factory basically working on agricultural products, and they were putting the waste from this process into the water. The water was basically drafting all that waste, which was a good source of food for the bacteria, towards jetties, and these bacteria were capable of producing pits in the body of the jetty as big as my head. So when you understand the source of the problem, then it is easy to solve it.
Well, now you opened our eyes, at least mine. Thank you so
You're
much
welcome.
for this.
You're welcome.
Now I will be worried about not only viruses, but bacteria as well.
But bacteria are much easier to deal with. It is viruses that, oh my God.
Do they cause corrosion?
No, thanks God. They do not cause corrosion. And this is a
At
good
least.
point out.
At least.
At
Well,
least.
thank you so much, Reza,
You're
for
welcome. Thank you.
giving this great talk. Thank you everyone for participating.